Okay, so today we continue with the category theory. As I said again, what one really cares about is that category theory for vector spaces, and as a parallel, as a basic example for sets. So let us do that. Okay, but so last time we defined what it was to be a category. It's just a sort of formalism. It's a language, and a category consists of two things. It consists of some objects, a class of objects. It was not really a set. It may be bigger than a set. But for every pair of objects, a set of morphisms, and then that contains the identity map. Every set of morphisms from X to itself contains the identity map on X, whatever that is. And then there is the notion of a composite, composing two morphisms, if the domain and codomain are correctly defined, if you will, and such that the identity map post or pre-composed does not change the morphism. And that's what it was. And basically everything that we will see is a subcategory of the category of sets, where the morphisms are functions. And so everything for us is the usual things, where objects are first of all sets with some extra structure. Morphisms are functions with some extra properties that preserve the structure. So that's what we are going to always see. So, and basically we will just look at sort of two categories: the category of sets and functions between sets, and the category of vector spaces over a particular field F, and linear maps, linear morphisms. These are what we are going to see. Okay. So that's what we are sort of effectively going to see throughout this category theory part of the course. So again, the reason why I'm doing this is I want to talk about the products and coproducts of vector spaces. Also about vector space duals or duals of vector spaces, and tensor products of vector spaces. Okay. And so duals will not be really category theory, but tensor products definitely will in some sense, in the sense of what is called a universal property. Okay, so without further ado, let's first start with products. So we know what is the product of a set, two sets. Right? If I give you a set of size 5 and a set of size 6, then I know that there is something called a product, which is indeed a set of size 5 times 6. That's called the Cartesian product, right? So let's start with products. Now what I want to say is that the Cartesian product of sets can be defined. You can also have the Cartesian product of vector spaces, and that is a vector space. The Cartesian products of sets are sets, and these constructions, these product constructions, satisfy very similar properties. Because that's what we are getting towards. So let's see. Yeah. So what we're going to start with, let's see. Yeah. Right. So the Cartesian. First of all, let's do this for sets. The Cartesian product of sets x comma y. Right? What is it? It is precisely the set this thing, right? And indeed, if and the property, of course, is that, and if let's say x has size n and y has size m, then x cross y has size m times n. So indeed, this is a product. Okay. Now, of course, this is so we all know this definition. So I'm not even defining it. This is known to you. Let me write down the product of an arbitrary collection of sets. Similarly, the product or the Cartesian product of a collection xi, I is in I, okay, is given by so you can just write this down like this. So you can define this to be the set of all tuples such that the ith coordinate belongs to the ith set. There is another way to write this down systematically. You can also say that this is equal to the set of all functions from I to the union of xi. I'm not saying that the xi's are disjoint. They may have some common intersection. That's fine. Such that f of I belongs to xi. Basically, this data is just what is this? What is this? No. So a tuple of sets, a pair, a triple, a quadruple, a n tuple is literally a function from this set to another elements of that, and that's exactly what this is. This f so is the same as saying f of I over all I. Right? A function is given by its values at every single input point, but that is exactly what I'm calling xi. So that correspondence is why these two descriptions are the same. Okay, so that's what really is the Cartesian product. So fine, of a family of sets. Now, do I want to say something about the thing for vector spaces? So maybe not. Maybe let me show you what this Cartesian product satisfies something called the universal property. This satisfies the following universal property. And universal property is, these are sort of phrased in a very weird way, but I mean not weird, very maybe unfamiliar with you guys right now, but I hope to show you, well, I will show you at least one more property like this in today's class, and maybe you'll see why, I mean, what's the point of these universal properties, so we will see that. Okay, so what is the property that this construction, this Cartesian product satisfies for sets? It's the following. Okay, so given any, let's see, so property or theorem or proposition maybe. Given any set x, so okay, so first of all, I'm given a collection of sets x. So we are given xi, I, and I. And any, let's say non-empty set z. Actually, okay, maybe I'll first show you the universal property for x cross y. So we are given this x and y. Now given any set z and maps, I guess it goes from x to z and y to z, yeah. So if we say phi, no, z to x, sorry. Yes, z to x and phi y from y to x, sorry, z to y. Right. So basically I'm drawing the picture, and I will draw the picture here. So given, I am given two sets x and y, and I'm given any set, so whenever I'm given these sets x and y, given a set together with maps, there is a unique map to the product, I think. So therefore I should draw this bigger. There exists a unique map. So first of all, notice that from x cross y, you have obvious maps to x and y. Right? Take the, whatever this thing, this is a pair of entries. Take the first coordinate, that's an element of x. Take the second coordinate, those are called pi, the projection is pi x and pi y. Now, given any such thing, there exists a unique map like this. Let's call it phi, such that the triangles commute. Meaning, if you start with an element here, apply the phi to here, and then take the first coordinate, that is the same as taking this phi x. Or apply this phi map, take the second coordinate, and that's the same as saying phi y. So you are given these maps. Given this set Z and these maps, there exists a unique map. There exists a unique map phi from Z to X cross Y such that instead of taking phi X, you could first have taken phi and then taken the phi X, and similarly for phi Y. Oops, this is not pi little x. It's pi X. And I should have defined pi for you, but so I can just tell you here. Here, pi x of x comma y is literally x. So this is a map from x cross y to x. And similarly for pi. This is the proposition. And the proof is obvious because we know the map. When I say there exists a unique map, I'm going to tell you the map. Define phi of z. Well, what can you do, right? You want the first, whatever you want, whatever this answer is, the first coordinate, whatever this answer is, it is some element of x comma y, right? X cross y. So it's some element of x, some element of y. But now you know what that element of x is because this map tells you that the first coordinate, the first element, must be phi x of z. And the second coordinate must be phi y of z. And therefore we are done. And that's so check unique, check it is unique. Check uniqueness, but I mean basically the fact that it must be is the uniqueness part. Okay, so now the point is this is not just true. I wrote this down as an introduction for two objects, for two sets x and y, but I can do the same thing for an arbitrary collection of sets here. And so let me do that more generally. So we are given those collection of sets. Okay, so more before I say that, more generally, given those sets xi, first of all, you can form the Cartesian product, but also you can define the maps pi xi. Define pi I, I'll just call it pi I instead of pi xi. From the product, let's call it pi I naught. I in I, xi to xi naught for I naught in I. So like take a specific element I naught and look at that particular coordinate. And it literally takes sending a tuple xi, as we called it, to just the I naught coordinate. This is clearly an onto map, so I can even say this onto. This is the notation for onto. Anyway, so these are the maps. So now let us write down the proposition. The proposition is again simple. So proposition. And I'll again draw the same picture. So now I'm given xi naught, let's say, or let's say xi here. Fine, let's say xi naught because of the notation. And then this is the product I in I, xi. Oops. So now basically we are saying given this map phi I, and this is the map phi I naught, given this map phi I naught for every I naught, there exists a unique phi. And again, you know exactly what the answer is. So, okay. So given all these things, so given any set Z and maps, let's call them phi I naught from Z to x I naught for all I naught, there exists a unique map phi from Z to the Cartesian product, to the product I, such that, okay, I should have done this better. Fine. So that if you compose, so that this composite is true. So that phi I naught, that's the exact thing, is equal to, first you take the phi and then you take the pi. Am I writing this wrongly? No. Phi. And this should happen for every single factor. And again, the proof for sets is clear. Literally, again, the same thing. Define phi of what? Phi of Z to be the tuple phi I naught of Z, phi I of Z, let's say. I in I. And check that it's unique. So exactly the same construction goes through. There is no difference at all. Okay. Now the point is the following. What is the nice thing about this property is it can actually be used to define the product. It is not just something that is satisfied by the product. It is something that defines the product. Okay. So that's what is called the universal property. Anything that satisfies this property is basically in bijection with the Cartesian product. It is basically equal in some. It is isomorphic to the Cartesian product because in the category of sets, bijections are isomorphisms. When if two sets are in bijection, that means they are really the same set under some relabeling of names. But the set itself is the same because the size is the same. So the same thing happens here. Right? So if you have two objects, two sets satisfying this property, then they must be isomorphic. And that is the nice thing about the universal property. So basically, in category theory, that's what happens in general. You write down universal property to define the construction, and automatically that guarantees that anything satisfying, any two things satisfying that property must be isomorphic in that category. So that proves uniqueness and basically proves everything else. It is equivalent to the definition. The only thing it doesn't prove is existence. And so you have to actually come up with a candidate with some specific example of an object that does satisfy the property. And in this case, yes, the Cartesian product as we have defined it does satisfy this property. Okay, so that's the point. So now what I'm going to say is, I'm basically going to say in a general category, you can define the product with respect to this as this. You can call this the definition of a product. And I think that's what I want to do. So, for example, let me say the following here. So, this property guarantees. Let me remove this part, right? So, okay, so the claim is any set of objects satisfying this property are isomorphic. So, any two sets. Remark, let's call this remark. Any two sets satisfying this property or this proposition are in bijection. Which is the same as saying i.e. isomorphic in the category of sets. But are there two different sets that satisfy this property? So let's say I have this x and y, right? And I just want to look at the product of x and y. Is there a different set that satisfies the same property? Think about it for a second. Pause the video. And for those of you who just want to enjoy the show, yes, there are. For example, e.g., of course, x cross y satisfies this property, But instead of here, I could have put y cross x. Let me write that in blue. And then I would not, then I would not call it pi x and pi y. I would just, so here it is called, let me call these as pi 1 and pi 2, the first factor and the second factor. But if I instead use y cross x here, this would be the second factor here and the first factor here. And with that map, it indeed works. So, e.g., x cross y, pi 1 and pi 2. This is, so you don't just use the data of the object itself, the set, but also these projection maps. That is part of the data of a product. Okay? And y cross x, with the data being now pi 2 here and pi 1 here, are both products. Both satisfy this property. Meaning they are both satisfy this property, and indeed they are in bijection. The bijection also is obvious. There's a unique bijection. Just flip the two factors, right? And these are in unique bijection. And there is a bijection, and they're bijection. I'm just saying they are in bijection. I'm not saying like what the bijection is, but yeah. We will see later why that bijection is unique also. But okay, fine. So this is what happens. You may have multiple different candidates. There was nothing special about x cross y being the Cartesian product. I could have taken y cross x. There is nothing special about x cross y. The point is that it is whatever I take, y cross x, x cross y, it is in bijection with x cross y. So x cross y is just one choice of which way to take the Cartesian product. But I could have taken the other choice as well, and that would not change the same property. That would not change basically working with the Cartesian product. Okay, so that's what it says. Now, the same exact thing happens with this property. But now let me call this a definition. Okay, so now we are going to define the product of a family of objects. So in a general category, in an arbitrary category C, we have, so now let me write down the definition of a product in an arbitrary category. Definition: the product of a family of a collection of objects okay, I will xi, I in I, is not just the object distinct, but the object together with these maps. All of that together is the product. Is xi is an object xi and morphisms whatever to from it to, let's even give these names. So let's say pi I belongs to morphisms of this object. Sorry, pi I naught, I in I, xi, and xi naught. Okay, so all these morphisms such that, okay, now I need to, I didn't find the space to write it, so I have to rewrite it. But basically, I'm writing down exactly this definition shifted one line. Such that it is such an object which satisfies the following property. Or this, it is an object this and morphism this, which satisfy the universal property which I had written down above or earlier. What is the property? Given any object Z in the category and morphisms phi I from Z to xi. So again, these are not really functions, they don't need to be functions, but we will just still denote them as if they're functions. Okay? There exists a unique morphism phi from Z to the product to that new object, whatever it is, such that these things happen. Sorry, this was supposed to be xi naught and phi I naught. There is a unique morphism from phi to I belongs to I, xi, such that the same thing happens. So either you can directly go from Z to xi naught, or you can first go from Z to the product and then go from the product to the xi. I'm not saying here these are sets and that that these are the component maps phi I, but basically we will see that for all I naught. So that is now the definition, not the property, because in the general category we have no information about such things. In particular, we don't know if products exist. Okay? They may or may not exist. So I think in the category of fields, you should check if a product exists. Okay? Okay, so we don't know that product do exist in every category. So I should say the remark. Products may not exist in every category, but if they do, then they are unique. Unique meaning, I'll tell you what. Let's try some other marker. Unique, but what does unique mean? Of course, they're not unique. We just saw that x cross y and y cross x are two possible products of sets. They're unique up to isomorphism in the category. Okay. Why is that? So, proposition. This is actually provable, and it's provable in like 3 lines. That's why I'm proving it. Proposition. Suppose, yeah. See the product I in I, xi exists in C. Yeah. Actually, sorry. Let me put it this way. Say a collection of objects, a set of objects, of objects in C has 2 different products. And by the way, I should have pointed, they're unique up to unique isomorphism. Even the isomorphism itself is unique. It's very, very precise. Okay? Has 2 products. Let's say, I don't know, x and x prime in C. Then there exists unique isomorphisms from x to x and reverse. That is the theorem, proposition. Well, let's call it a theorem. This is sort of important. That it's all unique. There is no ambiguity, possibility, redundancy, anything. It's unique. So why is that true? Why is that true? Fine, so okay, yeah. Okay, great. Yeah. So, sorry, 1 second. Let me just set the alarm so I don't forget. Okay, great. Yeah. So, proof. Let's see. Why not? And after we do this, so basically what it shows is the problem is we don't know existence. Whenever I use a universal property like this, we don't know existence, but we know uniqueness. And eventually I will define the coproduct, and for that there is a similar theorem. Let's suppose this has two coproducts, then again they are unique up to unique isomorphism. So that kind of thing happens for every kind of categorical construction which uses a universal property. What you don't know again in that case is, does a coproduct exist at all? Yeah. The same thing for vector spaces. If we can prove that a product exists, then by this completely general construction in any category, it has to be unique. But does a product exist for vector spaces? Meaning, is there a vector space that satisfies this property? We will see. The answer is yes, but we will see what it is later. Yeah, the answer is yes. The answer is yes for coproducts as well as for sets. So we will see those. Okay, but for now, let's look at the proof. So the proof says basically the following. It's literally very simple. You draw a diagram. So suppose that since there exists objects by the universal property, you can do the following fun. Right? So take any object. Let's call, what was it called? It's called xi naught. Okay. Now, first of all, it goes to x by this map. Let's give those maps some names. So let's go. Oops, something is very wrong. But you want the x's to go to xi naught. So the map should be reversed. So x goes to xi naught by pi I naught. Then you have x prime going to xi naught by, let's say, pi prime I naught, right? Okay, so now let's look at the property here, right? This is some product, whatever this is a product. So you are given this, then there is a unique map from this to the product. Well, this is a product. So this has maps here. This is given to have maps here. Remember, the product comes with that data. So if you are given two different products, they both come with that data. Well, so think of this as Z and think of this as the product. Z maps to this, the product maps to this, therefore there exists a unique map this way. Let's call that map phi. But similarly, I can think of x as the product and x prime as z, and then there exists a unique map eta. Right? There is no the same diagram. The point is, each of them plays the role of z, and each of them plays the role of the product. Therefore, there exists a unique map eta as well. And the point is, this happens such that the diagrams all commute. So eta and then pi I naught gives you pi prime I naught. Phi and then pi prime I naught gives you pi I naught. So by the universal property, there exists unique morphisms pi and eta as in the picture. Let's or phi. I'll write this down here again. Phi from x to x prime, and eta from x prime to x. Such that when you compose these equations code, You can do pi I naught. You can go directly from here to here, or you can first go to phi and then do pi prime I naught. And other way around, pi prime I naught, you can go directly, or you can first do eta and do pi I naught. And you can do this for every single I naught. But now let's look at the following picture. Now let me increase it slightly by just saying, let me continue along to x. Now, of course, that means again x. So let I look at both these pictures, but I don't twist them back. I just call this eta. I put that part here. There exists a unique eta. Oops, I don't have space for that. And there exists a unique eta here. There is unique phi. Right? So therefore I have this thing. And the diagrams all commute again. This was pi I naught. But then here is where the fun is. The fun is very simple. Space. The fun is that I look at this map. Maybe I should cover it in blue. Look at this map. From x to x. Clearly, since there is a unique map like this, the composite eta composed phi is a map that satisfies this triangle commuting. Right? So let's write down there. But then, first you do eta composed phi. What I'm saying is I can take x here. Okay, I can take x here and I can take x here as well. Then clearly x goes to this x I naught is the pi I naught map. X goes to x I naught is also the pi I naught map. So by the universal property, there exists a unique map here. Let's call that rho. There exists a unique morphism from x to itself that satisfies this. But do you already know a map that does that job? Is there a map that already satisfies that pi I naught is equal to some rho composed with pi I naught? Well, in a category where you have no information except the basic definitions, yes, we do know this map. And this is called the identity map. The identity morphism satisfies identity composed with pi is pi. That was part of the definition of a category. Right? So, but on the other hand, you see here, I just gave you a map eta composed phi, which also satisfies this thing. So because of the uniqueness part, eta composed phi must be equal to identity map. And that is what the entire point is. So let me erase this, just think of it there. Maybe I'll write it here. X, there exists a unique rho, pi I naught, x I naught, x pi I naught. Right? By the universal property, right? I can take z to be equal to x itself, and then I will get the identity map here. And that's what we say, identity x, both satisfy the diagram commutes, that the diagram commutes. So you can take rho to be this or rho to be that. Let me put it this way. I'll say rho equals eta composed phi and rho equals identity x, both satisfy that this diagram commutes. This diagram commutes. Commutes means that the equations are satisfied. And because so now the whole point was that this product by definition is something that satisfies the universal property. That means the product is by definition something that has a unique map. So by definition, eta composed phi is identity map. Also, by the way, this eta was the phi and the eta were unique already. The uniqueness is already proved here. Making the problem. So I should have said this is that making the diagrams commute. Okay, that's what. Of course, there may be other bijections between two sets, but there are only the specific ones that make these diagrams commute, and indeed they are inverses to each other. And the point, what I have not shown you, what I've shown you is there exist unique morphisms that make the diagrams commute. The problem is the iso part I have not yet shown you, right? So why are these morphisms? Isomorphisms, and that is basically because of this. Eta composed phi is the identity X. Similarly, by the same procedure, one shows that phi composed eta must be the identity of the other object. And so now because you have these ducks eta and phi that pair against each other and give you identities, they are both isomorphisms. Okay, so that's what it is. So the theorem is that whenever you have two different products in the same category, they must be isomorphic, and there are unique such isomorphisms that make these diagrams commute. The uniqueness was very clear because of the universal property, but they were morphisms. They were unique morphisms such that diagrams commuted. But then you can just compose the two of them and get from X to itself or X prime to itself by either identity map or by eta composed phi. And so by the uniqueness, once again, they must be equal. And therefore you get that they are both isomorphisms. Okay, so that's what that is. Now we can, very good. If I go, okay, so that was the product. And so what have we seen about products so far? We've seen the definition that we've seen that Cartesian products satisfy this property, which I have erased. And so that's a nice thing to have. Okay, that means the category of sets has a problem. So we saw that this property is not automatically satisfied because there is not enough information in a general category. But you can define it to be the product if it satisfies the property. And then the statement that Cartesian products satisfy it just becomes that products exist in the category of sets. Okay. Now the next statement was, so now once one defines the product, they indeed may not exist in every category, but if they do, then they are unique up to unique isomorphism. This unique was this part, unique making the diagram. Okay. And then the theorem says exactly that, and we prove it. Okay, so now I have only so far given you one example of a product existing in a category, which is the Cartesian product in the category of sets. We will see only two categories. We are only interested in the category of vector spaces, but as a motivation, I'm giving you the category of sets as an initial example. We have seen the products exist in sets. Let's look at products in the category of vector spaces. So example 2, as always, for category theory, we will look at sets and vector spaces. So again, because of universal property now, all I need to do is to prove the existence of a product, of some object that is a product. The rest of it is taken care by this theorem. It is always unique up to isomorphism. So similarly with vector spaces, it doesn't matter which category I'm working with. For a vector space, any two products will be unique up to linear isomorphism because that is the isomorphism in the category. So the whole point was it is unique up to isomorphism in the category. So if I know that one product exists, then any other product is a vector space that is isomorphic, linearly isomorphic to this one. So it really doesn't matter which vector space I choose; they are all isomorphic to each other. It's like choosing F2 or a two variable product or something like that. Okay, so see, well, example, maybe as a proposition. Products exist in the category of vector spaces. For all F. For every field, look at the category of vector spaces, then products do exist. And the proof is simple. The proof is just to give you an example of a product and check that it satisfies the defining property. Okay, and that example is simple. It's exactly the Cartesian product. Define. So given vector spaces, of course, everything is over F. Vi. Define product I in I. So we keep using this notation And that actually turns out to be the correct thing to use because of the Cartesian product, to be their Cartesian product. You can define whatever you want, but you must prove that that is a valid definition, that it satisfies the definition or the defining property, the universal property for the product in a general category. So, okay, so let's do that. So, given vector spaces, so given any other vector space, so first of all, is there a map? Okay, the claim is this is the product, so claim this is the product. This satisfies the universal property that defines the product. The universal property of a product Why is that so? Well, that is because proof. First, I need to give you not just this as a set, but as a vector space. I need to tell you this is a vector space. I need to give you morphisms to each of the individual vector spaces. So this is a vector space. This has to first of all be an object in the category, right? So indeed, it's a vector space under what? Well, it's obvious. This is just a bunch of tuples of vectors, right? So just take coordinate-wise addition and coordinate-wise minus and scalar multiplication under coordinate-wise operations. I'll write this down very precisely. So if I take two, so what I have to do is I have to take two vectors, vi. So each vi small is in capital Vi. Okay, I want to do C dot Vi plus Vi V prime I, let's say. And by restricting to various things, you can put 0. First of all, yes, maybe I should first say 0 is literally just a collection 0. 0 Vi or 0 I. Okay. Now C dot Vi plus Vi bar is equal to, you can guess, it is CVI plus VI bar in every single VI prime, every single coordinate. So this is what it means. Okay? You just do it coordinate by coordinate, and that's it. First of all, it's a vector space under these operations. So 0 is 0, minus is minus, C is C, plus is plus. Everything in each coordinate separately. Okay. Second thing I need, in addition to the this being an object, is the morphisms to each of the component objects. Okay, that is also easy. That is the same as the set morphisms. Just take the projection. B. So I have to define them for you. Right? So I have to give you the definition of these morphisms. So definition, define by I naught from product Vi to Vi naught. Yeah, that's also obvious. Take this pi I naught of this set is equal by definition to just a Vi naught. This is again just a definition. Like this was just a definition, but then you have to check that it's a vector space. Similarly, you have to check that it's a morphism in this category, meaning that it is linear. So I'll leave that to you to check, but that's sort of obvious from this definition here. Pi I naught is linear. Okay, so that's the second stage. And then part 3, now we actually have a valid candidate. Now that this is the object and these are morphisms, we have a valid candidate for the product. So now you check that it satisfies the defining properties. Now given a vector space Z and morphisms and linear maps. Morphisms in this case are linear maps, or even F linear maps if you want. Phi I from from Z to Vi, or phi I naught for all I naught. Again, you can check what's the unique map going to be. That's obvious again. Define phi from Z to V, so to the product of Di in the obvious only possible way. The coordinate eventually has to be this coordinate. So therefore, whatever this is has to be literally phi I of Z, I in I. And that is fine. I can write this here. Okay, great. Check that this is unique, check that this works, and then it's unique basically because this has to be private. This is the same thing as we saw. It's the same thing as we saw for sets, so there's nothing to say here. Anyway, that's how you prove that the products do exist there. And so again, one product is this product of Vi, but for two vector spaces, it would mean that it is V cross W, but it could also have been W cross V. There is no problem, and the map that takes V cross W to W cross V, the flip map, actually is a morphism in the category of vector spaces. Right? It is a linear isomorphism. So it's a very nice, that's the point of these maps and structures. Is there any, yeah, so that's the point. Okay, fine. So that was that. So wait, that's the universal property. Okay, so that is for vector spaces. Now let's do, so we have done products. Now let us do coproducts. And let's see how far we get. Let's see, fine. Yeah. Okay, so let's write down now the coproducts. Coproducts, the idea is whenever you see co in category theory, it means all the arrows are reversed. That's literally it. But now what happens is that constructions behave very, very differently. Okay? I mean, you'll see that there's not really a connection between the coproduct of sets and the product of sets in some sense. Okay, so this is done. So let's start from there. So similarly now I'm going to define for you a coproduct and then claim that they do exist in both the category of sets and the category of vector spaces. The sets being just an example to motivate the vector spaces. And eventually you want to get, as I said, to tensor products. Fine. We get there. So, okay, fine. Let's see how much we can do. So, yeah. So, definition. The coproduct, I'm going to define it in an arbitrary category now. Let's see which pen can I use, maybe this one. The coproduct of objects in a category. Again, let's say xi, I in I. Category C is again an object. This time, as I said, because all arrows are reversed, we also write the product in an upside down manner. That's what it says, that's what it is. And not much can be done about that. Sorry, I need to record this here. Okay. Okay, very good. Okay, so again, this is an object listing, but again, this is not enough. Also, we need maps. Now, in the product case, the maps went from the product to the objects. In the coproduct, they go from the objects, along with, together with morphisms. We'll call them eta I naught from X I naught to this coproduct, whatever this mysterious, satisfying the following property, satisfying the universal property. Following universal property. And again, we can guess what it is. Given an object, now instead of vector space, I would say object, and instead of linear maps, I would say morphisms, and the morphisms would go the other way. Given an object Z or Z, in C obviously, and morphisms, right? And this time the phi I naught will go the other way. So this time they don't go to from Z, but they go to Z. X I naught to Z. There exists a unique map. So now again I draw the same picture, except now I have to draw it the other way. So I draw again Z, I draw X I naught, and I have maps phi I naught. Yeah, and then there is, of course, there are the maps that eta I naught that go from X I naught to the coproduct. Then there exists a unique map going this way, which I'll call phi, such that the diagram commutes. There exists a unique morphism I and I, such that this diagram commutes. What is the diagram? It is that you can either go directly by phi I naught, or you can first go by eta I naught, and then go by phi, for all I naught. That is the diagram. Great. So again, this is a definition. Once again, you can prove that, again, the same kind of thing. You can draw pictures to prove that if coproduct exists, then it is unique up to unique isomorphism. So I won't prove it now because basically these are the same kind of construction. The same, you draw X and X prime, and you draw some arrows between them and check that the identity works and so on. But so remark or fact, lemma without proof. If the coproducts exist in C, then they are unique up to unique isomorphism. Then arbitrary category. There is no restriction on which category, then they are unique up to. And when I say unique, again, I mean unique making these diagrams come. The question is of existence. And again, they need not exist in every category. But in the two categories we care about, fields and sets and vector spaces, they do exist. Let's explore what they are for sets. In fact, and for simplicity, I'm just going to look at two sets first. Okay. What is the coproduct of two sets? Well, it's a set, so it's an easy coproduct. So it's like, I'll even give you an example. Right? So say x equals 1, 2 and y equals 3, 4, and 5. Very, very simple finite sets. I want to know what is their coproduct if it actually makes sense. Maybe it doesn't make sense. So what is the coproduct? Sorry, more water. Okay. So actually, okay. Now here I'm going to start for sets. I won't use X and Y. That is for a general category. Here let me use B and B prime. Okay. So what is the coproduct of B and B prime? Or let's even call them B1. Let's say B and B prime. So what we want is let me call it B1 and B2, and the coproduct I will call B. Okay, we want some set B. And some extra information, the morphisms, such that basically so if you take any function from B1 to subset Z and any function from B2 to subset Z, if given any morphisms like this is equivalent to some function from B to Z. So how can all of this data be gathered by functions from one set of data and no more information? It is equivalent to this. No extra information is here. This data gives you that data gives you this data. How can you do that? Well, what you must know is what is the value of f1 of 1, f1 of 2, f2 of 3, f2 of 4, and f2 of 5. So f2 is not defined here, f1 is not defined here. How can I take all that data together? All the data f1 of 1, so 1 and f1 of 1, 2 and f2 of 2, f1 of 2, sorry, still f1 of 2, 3 and f2 of 3, 4 and f2 of 4, 5 and f2 of 5. How can I take all this data together? Well, I can just take it literally together. And that would just mean that I'm looking at a function defined on the set 1, 2, 3, 4, 5. If it is being defined on 1 and 2, I take f1. If it is defined on 3, 4, 5, I take f2. That's all. It's as simple as that. Right? So all you need to do is, instead of looking at all these functions, that is the same as saying the set itself should be just 1, 2, 3, 4, 5. And the function itself should be f1 or f2, depending on what the domain is. And then that's it. So if you are given f1 and f2, then I can define my function exactly as f1 on these two elements, f2 on those three elements. We want a set. So okay, so that's exactly the point. That's exactly a choice of coproduct, and you can check that it works. So similarly, now let me just say, proposition coproducts exist for sets, and therefore, in fact, you can do this for a general collection of sets. Before I do that, and the answer is going to be exactly the same. It is the disjoint union of sets. It is not the Cartesian product of sets, whose cardinality is the product of the sizes. It is the disjoint union whose cardinality is the sum of the sizes. So some of the plus and the multiplication really come from products and coproducts in category theory, or coproducts and products in category theory. Okay, but so of course, if my sets are 1, 2, and 3, 4, 5, then life is good. I can take the disjoint union. But let me just make a remark. What happens if I have, let's say, 1, 2, and 1, 2, 3, or 1, 2, and 1, 8, 3? How can I take the disjoint union of 1, 2, and 1, 8, 3? You see, if I take this, I can write it as a multiset, 1, 1, 2, 3, 8. The problem is in there also, I cannot distinguish between the two ones. It's fine to write it as a multiset with two ones in it. But how do I know which of the ones is this one and which of the ones is that one? So you have to think of some way to formally, systematically be able to write it down so that you can unambiguously understand which one comes from there. So if this is B1, this is B2, how do you do that? And the answer is clear. What you do is the following. You keep a track of which set it's coming from. So for instance, the disjoint union of a collection of sets, even if those sets have some overlap, but then when you want to take the disjoint union or the coproduct, of a collection of sets xi I in I is going to be done as follows. I will keep track, as I said, of which set it's coming from, is given by let's say union with a dot I in I, xi, and I'm going to define this formally now as the set of pairs. Is a set of, sorry, I keep saying xi, but I want to keep saying bi, so let's say bi. I'm going to call I comma b such that I is in I and then b is in bi. The second coordinate, which set it lies in, depends on the first coordinate. The set that this lies in is indexed by the first coordinate. This is how we define it. Now, even if the b's are the same everywhere, even if all the bi's are equal to 1, 2, this first coordinate will differentiate between which one and which two from which bi. That's why we keep track. And now the proposition is coproducts exist in the category of sets. In fact, this is a coproduct, and therefore it is unique up to unique isomorphism. I and I, bi is equal to. When I say equal to, it just means that it is one of the candidates up to isomorphism in the category of sets. This is not in the category of vector spaces, just in the category of sets. Sorry. And again, the proof I will I'll sort of sketch it or say it, but it's really the same thing. And once I define it this way, it is really very, very precise. So the proof is literally given a map. Okay, so given. So first of all, I need to. So clearly, this is a set. What are the maps defined? So I need to define the maps. Define eta I, and these are functions. So the moment I define them, define the function under isomorphism from bi naught to the disjoint union of bi. And this is obvious when I define it that way. Eta I naught of bi naught is given to be, obviously it has to be placed in the I naught position. Yeah. That is obvious. This is clearly a map of sets. And now, as far as the universal property goes, given any set Z and any morphisms, any functions or any maps, so this is called 1, let's call it A, will be given a set Z and maps. There's one. Morphisms in the category of sets are just any functions. So let's say these are, I want to call them phi I naught from bi naught to Z. I need to define a map from this coproduct to Z. So define phi from the coproduct. This dot stands for disjoint union, by the way. How do you define it? Well, that's obvious. Phi of I comma b. Well, I comma b means that the b has come from the bi. Or let's say I naught comma I comma equals. So by definition, this equals. If it's come from bi, then I use phi I. For all I in I and b in bi. Check this is unique. Check this works and is unique. Because again, what can it be? What can phi of I comma b? So the point is you're given that these are the maps, right? So once you have this map is defined, then it's very easy to check that it must be exactly phi I of. Okay. So this is the coproduct in the category of sets. And now for the promised coproduct in the category of vector spaces. What is it there? Is it also the disjoint union of vector spaces? Well, the union of vector spaces is not a vector space. For example, I could take the x-axis and the y-axis with a disjoint union, so I keep the origin separate. That union of two lines is not a vector space. You can't add things. So what is the union of vector? What is the coproduct of vector spaces? That's not immediate, but okay, fine. The point is that it is so I will do this part and then motivate the tensor product, and probably that is where we will stop. Let's see. So, what is the coproduct of vector spaces? Well, the point is there is a different construction which works for vector spaces, and it is similar to the coproduct of sets in the following way. The B's are sort of like the bases. So if I have a bunch of vector spaces whose bases are Vi, then the coproduct is a vector space whose basis is the disjoint union of Vi. So that's what it actually satisfies. Okay, so I'll state that as a property and prove it. For now, let me just define the coproduct. Okay, so maybe I'll write that down as a proposition actually, or a theorem. One, coproducts exist in the category of vector spaces. And I will just write vec F, obviously. That's the category of vector spaces. Second, if Vi has a basis Vi for all I in I, this is a set. Basis is just a set. Right? Then, now because the coproduct is that way, has a basis, I can't say that the basis is equal to the coproduct of Di, because I can have any, I can have any arbitrary kind of construction of a coproduct. But these are all isomorphic, and similarly the bases are in bijection, they are isomorphic as sets. So I can just say has a basis in bijection with, or in bijection with the coproduct of the BS, which is the disjoint union of BS. That is the theorem we are about to prove. Okay, so let me just say that. So I need to define for you what that coproduct is, right? So just like here we defined the disjoint union by this way and then said that that was a coproduct. So similarly, let me now define it, and this is called the direct sum. It's not called the Minkowski sum, it's called the direct sum. It is smaller than the product. So it is a subset of the direct product. It's a subset of the Cartesian product of vector spaces. So proof. Every time I say proof, I'm sort of leaving something to you, right, to verify that something is unique. So define, so let's start with one. Define the direct sum of a collection of vector spaces of, actually I sort of can just say of vector spaces Vi. Sorry, not capital. Vi, I in I, to V. So it is defined, it is denoted by this thing. It is defined to be the collection of all tuples of vectors as in the Cartesian product. So take the Cartesian product, it is the collection of all such tuples. Take only those tuples which have finitely many coordinates non-zero. So all but finitely many coordinates are zero. So Vi non-zero for only finitely many I. Sorry, okay. For only finitely many I. This is what is the Cartesian product. Sorry, this is what is the coproduct. which is what, so, well, I have not told you it's a coproduct, I have just defined it with a direct sum. And so, in fact, that was the homework problem. So, homework, obviously, what if there are only finitely many i's? Then every vi can be non-zero, therefore, this can be the entire set. Right? So, if I is finite, I don't know that this is the homework. This is probably obvious. Let's not call it a homework. This is just obvious. Oops. If I is finite, then this is exactly equal to the Cartesian product itself. Okay, that's obvious. Now for the proof of the theorem. But okay, if I is infinite, then this is not the Cartesian product, right? Because I can only take finitely many non-zero coordinates, but the product of vi can have every coordinate non-zero. So there is no guarantee. In fact, it is strictly bigger than the Cartesian, than the direct sum. Okay, fine. So now for the proof of this theorem. So proof. Oh, okay. I just defined this. Fine. So continuing on the proof, the claim is that this is the coproduct. Again, when I say equals the coproduct, I just mean that it satisfies the universal property of being a coproduct. Okay, let's see that. And the part 2 we will discuss later. But so okay. So given now again. So first of all, is this a vector space? So we have to verify all those things, right? So proof. A. Indeed, this is a vector space. Why is it a vector space? It is a vector space because this is capital V. I should say that. The proof. The vector space, part B, maps eta i's exist, linear, and part C, universal property. So why is it a vector space? It is a vector space because first of all, is the origin in there? What was the origin? What was the zero in this vector space? It was with all the coordinates zero. So indeed, there are only how many coordinates are non-zero? Zero. Zero is finite. So that's fine. Indeed, yes, 0 equals all zeros. All zeros belongs to this direct sum. That's clear. And now, if I have any vector with finitely many non-zero coordinates inside here, any tuple, if I take a scalar multiple, then everything that was 0 will remain 0. Everything that was non-zero will remain non-zero if the multiple is non-zero, if the scalar is non-zero. So scalar multiples, yeah, this is closed under scalar multiples. Is it closed under addition? Well, if you have finitely many coordinates non-zero in some tuple, and finitely many other or overlapping or not, I don't care, coordinates in some other tuple, vi prime, then when you add them up, then at most finite union finitely many coordinates remain non-zero. And then you can check that the axioms of a vector space are satisfied because, yeah, you can check all that. So, check. So I told you the easiest one, 0 is in this space, and I'll tell you check the rest. Check the other axioms. But it's basically completely bookkeeping. This is like first week 1 kind of question. So that's why I'm not even asking you homework. But you can check the other axioms. Okay. So 0 equals 0 and bullet point number 2, check the other axioms. The second thing I need to do is to define the linear maps eta I. Let's do that. So define eta I. Eta I naught from V I naught to the direct sum. How do I define it? Via eta I naught of V, let's say I naught, This is a vector in Vi naught, capital is equal to Vi, I in I, where Vi is what? Each coordinate. It's very simple, right? You keep the Vi naught in that coordinate and you keep 0 everywhere else. Vi naught for I equals I naught, so that I don't have space. And if I is I naught, then it's Vi naught. Otherwise, else it is 0. Okay, great. Define eta I naught, Vi naught to be. Fine. The claim is this is linear. Check. I won't even check. This is really week 2 stuff. Right? So check eta I naught is a vector space map. Okay, it's very trivial to check. I mean, it's literally the same vector space sitting in one coordinate and everywhere else is 0. So for example, eta 3 of let's say 5. So all VI's are equal to R. This is literally the third position. Now, if I want to check that something is linear, then it's like saying, now I can say, let me even say, not all VI's are R, VI's are vector spaces. Now, if I want to say CV plus W here, CV plus V prime here, and put CV plus V prime here, it's really trivial. You can check that. Okay. And the final point is the universal property. That is the real thing to check. So that I will tell you. And fine. And then we do the basis thing, and then we are done. I think that will be enough for today. Yeah. And the universal property is simply that. Okay. So given. So first of all, that means this is indeed a vector space with a collection of morphisms leading into it, right? And now given maps from given given maps phi I naught from Vi naught into a map Z, into a vector space Z, right? Define. I want to define phi, lin of phi I, lin of the direct sum how do I define this? Well, there's basically only one way such that you would recover these things, right? So if you take any map, if you take phi of Vi1 plus dot dot plus Vin. So remember that only finitely many coordinates are non-zero. So let those coordinates be indexed by I1, I2, In from the set I. And let those be non-zero vectors. And of course, if all are zero, then I can say, first of all, I can say phi of the zero vector is the zero vector. That is obvious. It has to be linear, so of course it should take 0 to 0. But also, if something is non-zero, so all Vi is non-zero, so not equal to 0, not equal to 0, there is at least one coordinate and there are n coordinates where they're non-zero, then what should this be? So you want it to be something in Z. Well, it's basically saying, well, for the Vi1 coordinate, you take this map. For Vin, you take this phi I1 of V1. And now inside the same vector space Z, there is no more direct sum or whatever. These direct sums basically mean the following. I should have said maybe. What is this supposed to mean? It's supposed to mean I take a vector whose 0 Vi1, and 0 0 Vi2, and 0 0 Vin. And and everywhere else you have zeros. So there are only n many vectors in positions I1, I2, In, comma, 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 and this should just be phi I1 of V1 plus phi I2 of V2 plus dot 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 plus phi In of Vn. Once you have this definition, you can, again, I'll leave it to you guys to check that this works, this is unique, so on. This is a linear map, that it's unique and satisfies the condition. One can check, or you can check, or somebody can check that it's a linear map. It's a unique map, linear map. Satisfying the universal property. Sorry, this is the first part. And then let me do the second part, and then we will stop for today and talk about tensor products next time. Okay, so this is part 1, part 2. Which is that if you have Bi to be a basis of Vi, then the disjoint union of the Bi is the basis of the disjoint union of Vi. Okay, so or in bijection with. Well, that's fine. I think the disjoint. So in this case, certainly for this one, it is true. Okay, so except for the fact that the Bi's are a basis of Vi, so they belong to Vi, but Vi is not sort of here. So I need to use those same eta maps to define the BIs in bijection. So okay. So let's start by defining those eta maps. Okay. So now define the set B. So this is a subset of the direct sum. And this is going to be my basis, but I'm just going to take it to the union of the BIs, defined cleverly. It is a set of all eta I naught of B I naught, the collection where I naught, of course, is an element of I, and B I naught is in B I naught. So this is literally saying, well, I look at all these distinct elements in the I naught position, and for different. So I look at all the elements of B1 in the first position in zeros. So it's like saying, B1 0 0 0, and then B0 B2 0 0 0 0 B3 0. Let's just do this. Let's just do 3 of them so that I don't have space. And as long as my B1 runs over all elements of B1, my B2 runs over all elements of B2, and my B3 runs over all elements of B3, these are clearly distinct elements. And moreover, they are in bijection with B1, disjoint union B2, disjoint union B3, because they are at different positions. There is no overlap. Okay, so then B is in bijection. So I'll just say isomorphism or bijection with the disjoint union of the VIs, because they each occur in the ith position, which are distinct positions. Okay, and now the claim is this guy, this B, is a basis of the direct sum, and therefore, indeed, the direct sum has a basis in bijection with the coproduct, which is this thing, has a basis in bijection with the coproduct of the VIs. That's what it's saying, right? So, okay, that's the claim. I think I'll just do the span, but linear independence is equally simple. So, what is the time? Yeah, just do the span. So, proof. Basically, let me tell you why the linear independence is simple. Suppose a linear combination is 0 of these guys, right? Then in every core, it's a finite sum, so there are only finitely many places where these guys occur. But now in every single core, if a linear combination is 0, inside, well, all these elements are tuples. So if a linear combination is 0, then it is 0 in every coordinate. That means you look at all the summation part that is in the first coordinate, that linear combination must be 0 itself. then this linear combination must be 0 itself in the second coordinate, and the third coordinate, and every ith coordinate. But these guys are a basis of V1. So any linear combination is 0. All the coefficients must be 0 in the basis. And these guys are a basis of V2. So if a linear combination is 0, all the coefficients are 0. And so on for every coordinate. And so you directly get all the coefficients are 0. So linearly independent, I won't check. I mean, I just told you, and you can write it down. Spanning set is easy, so that's why I will write it down. So take any vector. So take any vector in so given V equals Vi in the direct sum. No, clearly 0 is in the span because 0 is 0 of anything. 0 times anything plus 0 times anything. Let's look at a non-zero vector V. Let Vi1 in Vi1, Vin in Vin be the non-zero components of V. Of the vector V, right? But now each Vi1, the Vi1 is a linear combination of these guys. So okay. Let me put it this way. Let's write down formally what that means, which is what I maybe should have done here, but fine. Now you can see what I was really doing there. So i.e. V is equal to summation j goes from 1 to n eta ij of Vij. Right? This occurs in that position. That's why I'm saying eta ij, to make it occur in that position. But now each eta ij of V, because this eta was a linear map, this is Vij is in capital Vij. And so each eta ij of Vij, or Vij is a linear combination of the basis vectors of Vij. Vij is in Vij, which is the span of Vij because it's a basis. And so you get a finite linear combination in each summand. Each of these guys is a finite linear combination, and therefore it is a finite linear combination. And therefore overall the V is a finite linear combination as well. Okay? And so rather what I should say is eta ij of V is the span of eta ij of Vij, because it doesn't matter. Eta is linear. And therefore, now each of these guys, this whole thing belongs to this guy, which is in the span of this guy, which is, of course, the span of the subset is contained in the span of B. And this is just part of the basis B, part of the set B. So the span of a subset is, of course, contained in the span of the set. So the whole thing is contained in the span of the set, because everything is a finite set. And so indeed, this guy is both linearly independent and it spans the coproduct. And therefore it's a basis. Okay, so that's it for today. We talked about products, coproducts in the category of sets, in the category of vector spaces. We looked at universal properties and we proved the existence of all these things and the connection between the product of sets is a set, the product of vector spaces is indeed the Cartesian product again. For coproducts, it's more subtle, but what we still do get is that if you have a set, if you have a coproduct of vector spaces, then the basis for that is given by the coproducts of the individual basis vectors, basis sets. Okay, so that's it for now. More next week. We will continue with this categorical stuff next week, I guess.